Good morning, and thank you very much for coming here and also online. So this is our computational social science webinar organized monthly by the Computational Social Science Lab at Chinese University of Hong Kong. And today we are very happy to have a speaker, Professor Liang. Let me introduce a little bit about Professor Liang. He's currently emeritus professor of the Department of Geography and Resource Management, and also honorary senior research fellow of the Institute of Space and Earth Information Science at the Chinese University of Hong Kong. So he's a pioneer of the theory and applications of physicist approach to geographical research and has done novel research on uncertainty and analysis, artificial intelligence, and machine learning. He has published 6 monographs and over 200 articles in international journals in geography, artificial intelligence, computer science, and information science. So as you can see that his work is very related to the computational social science. So without further ado, let's welcome Professor Liang. Okay. Yeah. Sorry, one more. For the online audience, so if you have any questions during the talk, you can just feel free to post in the chat box, and then later in the Q&A session that I will pick some for Professor Liang. Okay, yeah, thank you.
Okay, Professor Liang, thanks for the introduction. Okay, now it is my pleasure to be invited to give a talk. Okay, now what I would like to explore with you are issues concerning digital twins and the ways or possibilities that we can go about developing digital twins for social science research. Yeah. Now, I don't pretend to be an expert in various fields under the umbrella of social science, but I would like to give my layman perspective on how to make social science a research vehicles for different fields under the umbrella of social science. Okay. Now put a question mark in my topic because I think I might be raising more questions than answers in my talk. Okay. So that will give you some room for imagination and then some food for thought. Okay. Now, what I would like to start out with is digital twins for cities, the digital twins of cities, which I'm more familiar with. And then I would like to branch out into other fields of research in social science. Yeah. Now, because the topic is rather involving, so I would go for breadth instead of depth. So in other words, I will be skipping a lot of technical details. My choice is I would rather give you a whole picture of my research in this area. Okay, so now let's. Okay, now what I would like to invite you to look at is this painting. I suppose almost all of you know about this painting, right? What I would like to ask is, what caught your eyes the most in this painting? It's from Van Gogh, right? The sky, maybe, right? The curves in the sky, maybe the 3 circles surrounding the stars and the crescent moon, right? So that might be one of the eye-catching things about this painting. And I would like to have you to look at this photo. What do you see in the sky? Something very similar to what is put down in Van Gogh's painting, right? Curves in the sky. This is a real life photo. Okay. Okay. And I would like you to look at this simulation. Does it look something like what Van Gogh put down in his painting? Okay. Now, when we look at something, such as the paintings, we see something. We may want to ask, what is the underlying process or mechanism behind this pattern, right? Okay. For example, in Van Gogh's painting, so some physicists found out recently that it actually portrayed quantum Kelvin Helmholtz instability in fluid dynamics. Okay. So when two liquids come into contact with one another, one is at a higher speed, the other at a lower speed, then it will create the kind of turbulence that we see in Van Gogh's painting. Okay. And actually, it is the beginning of a chaotic behavior of the atmosphere. So, and some other group of researchers found out that actually, in the starry night, okay, the sky, it follows Richardson-Kolmogorov's cascade picture of turbulence. Okay, so you have large worlds and then smaller worlds. Okay, and actually, it is what the Richardson-Kolmogorov's cascade is about. Okay, it is a chaotic behavior. Okay. That follows the scalar law. Okay, so, and I would like you to look at this picture also. This is the current, right? Can you see some curves? Okay, in this thing. What about the atmosphere? Similarly, we have this kind of curves. Okay. Again, it's the turbulence in the atmosphere, even in the sun. Okay, that is the KH instability in the sun's atmosphere. Okay, that is captured by NASA. Okay, you may wonder why I want you to look at these paintings or these photos. Okay, let's come back to the Earth. Right? This is maybe the traffic condition that we often see in cities. This is crowd movement again. And this is the microclimate in cities, particularly high density cities. We see some pattern. Right? And this is how things circulate within the city. And maybe inside the house, we have some kind of turbulence also. Right? Okay, why do I want you to look at all these? Because it is our curiosity, right? We look at something, we see some pattern, and then the next question that comes into our mind will be, what drives this pattern? Okay? What makes this pattern occur? In other words, what is the underlying dynamics? Right? What is the underlying process? So this constitutes my research. Okay. So what I would like to do is to come up with a system that we can capture and learn the dynamics and complexities of our systems. Okay. City is a dynamical, complex system. Right? There are a lot of processes going on that drive the occurrence of patterns that we see. Transportation, microclimate, even social network, okay, all these phenomena. So we wonder what is the underlying process. Right? Can we unravel the underlying process? Or can we make a system to learn these dynamics and complexity? Right? Okay, so that's what constitutes the research in digital twins. Nowadays, digital twins concentrate a lot on information infrastructure, IoT. To me, that is essential, but not the most critical. The most critical is, do we have theory in digital twins? Just equipping ourselves with IoT, advanced information technology, would not make us that much smarter. What makes us smart is the theory. Right? Without the theory, the information structure cannot do that much for us. Right? So the whole research is how to integrate theory into digital twins of cities. Right? Okay. So that's the essential thing. So what we would like to make is, we would like to trace the system for the whole life cycle, not just one point in the time. I would like to model this system along its life cycle. Right? I would like to be able to update my knowledge and my model so that I can simulate the whole system throughout its lifetime. Right? That's the essential part. Okay, then what is digital twin? I touched a bit on it. These are different definitions. Right? At the very beginning, it is just what we like to do is to produce a virtual replica of our physical system. Right? It started out in manufacturing. We want to manufacture something, a car or something like that. Can we build a digital twin for the car? Okay, so it will be a virtual replica of our physical system. Later on, it is conceived as something, as something that we can work on. It is the structure, context, and behavior of an individual or unique physical asset. Any physical asset that we are interested in. Okay. We can build a virtual representation of it. Right? Okay, so what do we want it to use for? Is dynamically update with data from its physical twin throughout its life cycle. So in other words, there will be an interaction between the physical twin and the virtual twin. Right? That's what we call the digital twin. So the way to understand is, we build a virtual replica of the physical objects or system that we are interested in. Okay? So that's the original idea. But later on, we would like to do something with it. Okay? Could it help us to understand something? Okay? So, and once we can get a grasp of it, we would like to make it a useful tool for our decision making. So later on, we emphasize on the bidirectional interaction, just like what I just said. There has to be an interaction between the physical twin and the digital twin. And recently, people just conceptualize it as a model of some physical object, some physical process. Okay, so these are the definitions of digital twins. Later on, towards the end of my presentation, I will give you my definition of digital twin. Okay. Now, what I would like to outline for you is the whole conceptual framework behind the development of digital twins of cities. This is what we're interested in, urban dynamics and capacity. Right? What we would like to do is we would like to model the dynamics and capacity of urban development. Right? Okay, that's what we want to understand. How to look at it. We look at the urban system, we ask a question. If I see something, if I see a phenomenon, okay, if I see a phenomenon, I like to walk around. So if I see a phenomenon, I would ask, are there governing equations for this process? Do we have an equation like a differential equation, okay, that describe the dynamics of the system? If we do, it's good, but oftentimes these equations are very complex, very complicated, right? So can we sample from the approximation given by these governing equations? Let's sample it at different points in time. Okay? And then what the idea is, can we simplify it? Make it simpler so they will be more efficient to represent my system and to do a simulation, prediction, control, right? Okay, so this is what we call the reduced order model. Okay, that is the first perspective on this. However, because the capacity of city development, we may not have an equation for it. We may not know, it's too complex, right? So without governing equations, I don't quite understand the underlying process of a particular development in a city, right? Or I have very limited knowledge on it. Then what should we do? We should build into the digital twins, again, a reduced order model, right? Okay, what can we do without theory, without an equation, without a model? Data, right? Can we learn from data? Can we unravel the underlying dynamics from data? Okay. So we have observational data, oftentimes in time series, because we're tracing the development of city, right? So it's a dynamic system, so we need time series to do it. Once we got this, then we can do data-driven learning. Can we learn from data? All this data-driven thing will come into this. So from this, hopefully we can unravel the governing equations, right? And then once we get this, we'll be asking whether I can further simplify it so that it will be more efficient for me to do simulation, prediction, and control of the system, right? Somehow we want to control our system sometimes. We want to steer it to a desirable state, just like transportation. I don't want to have traffic congestion. Can I steer my system so that I can mitigate or even avoid traffic congestion, right? Okay. Now, this is purely data-driven thing. But oftentimes, data-driven learning is a black box. It's difficult to interpret, right? Okay, so here is can we instill theory into our data-driven learning process? That theory guides us to do data mining, to do data-driven learning, right? So that we can interpret the result, so that I know the result that I get from data-driven learning comply with theory, right? Okay, it's not a blind search. It's not something that is a black box. We want to instill theory into this black box learning process, right? So this is what I call theory-informed data-driven learning. Okay, and then again, we would like to find out, to unravel the governing equations and then reduce it, to simplify it. Okay, this is one way to look at how we tackle urban dynamics and complexity. However, when we look at our system, particularly city, we can conceptualize it as a dynamical complex network. So the whole thing is a network. When we look at social network, when we look at transportation network, communication network, okay, the whole thing. Maybe I can conceptualize city as a dynamical complex network. Okay. So what do we need to do? If I conceptualize it in this way, again, we need to have a matrix of interaction because it's network, right, with interaction. Similarly, we would like to ask a question: can I simplify my network so that I can make it more efficient for my analysis, such as simulation, prediction, control? Right? Okay. And we look at this. This seems to be a macro approach to look at urban dynamics and complexity. Somehow with a macro governing equation or set of equations that we can use to capture the macro aspect of this dynamics and complexity. What about individuals, particularly in social science? We are dealing with people, with individual objects, right? What about the bottom-up approach? Instead of a macro approach, I start out with the governing equations, and then I study the dynamics and complexity, and I build it from bottom up. Can I treat each individual as an agent? Right? And then I study it. So another way to conceptualize this is, let me look at it as a multi-agent system. Okay. Again, we ask this question: if it is a multi-agent system, can we have a governing equation? Even for multi-agent system, we still can develop macro equation for the system. Right? This is this one. Again, we would like to ask a question: can we reduce the complexity of this system? Okay, this one. However, we are more familiar with agents that can communicate with one another with some communication protocol, that kind of thing, right? Can we build communication protocol into the multi-agent system so that let it interact, right? Interact with one another, interact with the environment, and let the complexity and dynamics emerge through this interaction. Right? Maybe I can capture the governing mechanism of a system. Again, we would like to ask, can we simplify it? Okay, now that's roughly the whole framework that I'm mindful of the time, right? Because I have 100-something slides over here. So, okay. You may wonder why I always ask, can I do dimension reduction? As what Einstein said, okay, everything should be made as simple as possible. Simplicity is the most beautiful thing. Don't complicate things, right? But not simple. Too simple, we cannot capture the thing that I'm looking at. We make it just simple enough so that I can capture the essential, the most important aspects about the system. Right? That's why we always ask, can we do dimension reduction? Okay, all things I'm looking at. Okay, now I would like to briefly go through the hopefully the whole framework, but I'm afraid I would not have enough time for it. But I try to be as brief as possible. Okay, what I would like to start out with is building digital twins via intrusive models. That is the first aspect. We have governing equations for the system. Okay, how can we build a digital twin that can work on the governing equations and do simulation, prediction, control? I always use this because that's what we want to do for digital twins. It's different from models, right? Because that is what we need to do for digital twins. Okay, we look at this. You can see it. Land use transition, right? Yeah. This is something captured from remote sensing. You can see there how land use changes over time. Okay, these are some snapshots of the land use transition process. Okay, what makes this transition? What is the underlying mechanism for land use transition, for land use change? We want to ask this. Okay, we did some many years back, we did some cellular automata simulation. Right? Now, at that time, the way that I look at it is cellular automata, the canonical one, we just specify some rules, right, for it. But why these rules? Why? Actually, if I look at the result, I can make some rules and guarantee that the result will occur, right? Okay, but that's not the way that we should go about doing this. To me, we should start out from theory. What is the theoretical background or theoretical basis for land use transition? Maybe in the cellular automata, there is one essential rule, a simple rule like this. If build-up value, if a potential land value is greater than the build-up value, that is, there are potential for development. If I develop this piece of land, I will get higher value, right? Then this gives us the incentive to develop that piece of land. Now, this is based on rent gap theory. Of course, there are other theories of land use transition. I'm just using this as a basis for discussion. I'm not saying that this is the only theory that we should use, right? Okay. Based on this, then rent gap appears and land use change is likely to take place. Maybe there's a rule, how to realize this rule. Okay, don't worry about this. Okay, this is a stochastic differential equation that we developed for the description of land use transition. Right? Now, what it contains in here are these. In the equation, we build in potential ground rent, interest rate, GDP per capita, right? And then the volatilities of interest rate, GDP per capita, potential ground rent, and then the correlations between these three variables. That's what that equation contains, right? So that's how we describe the dynamics of the land use transition. Right? Okay. If we have this equation, then what do we need to do? We need to use it to approximate, right, the land use transition process. The approximation, if you're familiar with differential equations, we need to discretize the equation, right? Maybe finite difference, finite element, okay. We give an approximation, which turns out to be very involving and complicated, right? It can involve very high dimensions, a lot of parameters that we need to do, depending on how we structure the mesh that we use for approximation, right? Okay. I'm skipping all these. Okay, these are the boundary conditions that the differential equation need to satisfy. Okay. Okay, this comes back to us. This is too complicated, too time involving. Can we simplify it? Okay, so that's what we want to do. Reduce order models. Can we reduce dimension? Okay. Okay, in terms of reduced order model, it can mean these things. Perhaps we can use a coarser discretizing mesh, okay, or to find coarser to lower my computational capacity, right? Or we use a larger time step for approximation, or we can simplify the theory itself, use fewer variables to describe the same system, right? These are what we call the reduced order model. In other words, the whole thing is trying to simplify my model structure and try to make my approximation simulation more efficient. Okay, now I need to be fast. Okay, the purpose of all the reduction in models I just explained. What we want to do, we believe that for a solution of a complicated equation, there's a low dimension space, right? Okay. Low dimensional solution manifold. In other words, to get around the curse of dimensionality, we reduce the dimension, right? So in other words, we are looking for the low dimensional manifold for the solution of the equations, right? So essentially what this one means. I have to be fast, okay. So offline, we do the Offline, we do the low dimensional representation, and then online, we use it as a surrogate model, okay, for making my solution more efficient and my prediction simpler. Okay, that's the essential idea. How to go about doing this? I would skip all these technical details, but I just explain this to you. This is my original system. This is my reduced order model for the original system. The whole idea is we would like the difference between the solution of these two systems as small as possible. The majority of machine learning is based on this. Because we use machine learning, we have an estimated result, and then we say, is this result reliable? Okay. Then we say that the difference of my estimated result with the original result should be as small as possible, right? So it's loss minimization process. So that's essentially what it means. So this is the reduced order thing, okay? That is the reduced order model for this. And I want the difference to be as small as possible. Right? How to go about doing this? We need to create a snapshot matrix, just like what I just showed in the flow chart. Okay. Let me do some time simulations. Sample on it. Create what we call a snapshot matrix, on which we do the learning. Right? Okay. And let me skip all these details, okay, because we need to use a separation variable thing. So to break it down so that I can represent this original system by this process. Right? So imagine it, think of it as something similar to principal component analysis. Have we done simple component analysis? Okay. So actually the foundation of it is the singular value decomposition. Right? We use the eigenvector, eigenvalue, stuff. Just think of it as something like principal component analysis. Right? We want to reduce the dimension, right? Okay. So in other words, actually we're projecting my original system onto another coordinate system, which is simpler. Okay? That's the whole idea. So we call this. So I will skip all these details because I want to. Okay, this is the thing that we want to represent like this, right? Okay, these are the eigenvectors. Okay, matrix. This is the covariance matrix, something like that. Right? Okay. However, the dimension cannot be reduced that much. Right? Essentially, in principal component, you should have as many principal components as you have as variables. We do not do any dimension reduction, but we can truncate it. Right? Get rid of those principal components that are not significant in terms of explaining the variation of my system, right? Okay, so if we do truncation, I will skip this. This is a truncation, okay, of the original reduction. Would reduce the dimension. Okay, as I said, I would like to skip the details. So the reason that we can do this is based on the Ecker-Young-Mirsky theorem. Okay. This is a truncated thing. This is the original thing. Again, we want to make it as small as possible. The truncated representation is not that much different from the representation before the truncation, right? So that's how we reduce the dimension. Okay, this is truncation. Instead of M, I truncate it to R. So the matrix is of order R instead of M. That's how we go about doing this. Okay, let me summarize what we have just done. We start out with urban dynamics and complexity. So we have the governing equations. This is a high dimensional approximation, too complicated. And then we say, okay, let's sample on the approximation given by the high dimensional model. And I want to reduce the dimension. So I have a snapshot matrix, and then I do dimension reduction through singular value decomposition. Okay, and then you reduce all the model. So the purpose is to make my simulation prediction control of dynamics and capacity of cities simpler. Right? It's the whole idea. Okay, now, in other words, what I've just gone through is just this. The first part. That is when we have governing equations. Okay. How am I doing with time? I should finish at 11:30. Wow, it is only the first part. Okay, now let me let me go through it quicker. Okay, just give you the basic idea instead of details. Okay, now I would like to get into this part. I would like to get into this part. What if we don't have the governing equations? We just have data. How to go about doing this, right? Okay. So what we would like to build into the digital twins, the governing equations from data, right? Can learn this from data. Okay. That is what we call the non-intrusive models. That is, we don't have the equations for it. Right? Okay. Skip this. Now, there are several approaches that we can use to do data-driven learning. One is called the sparse identification, parametric mixture distribution neural network, and hybridization. I can hybridize these and form a better method. Right? Okay. Sparse identification. Let me briefly explain what it is. Okay. This is the original system that we try to solve, approximate. So what we want to do is, can I simplify it? See, this is a simplification of this through sparse regression analysis, right? And this is the sparsity. Okay. So what I want to do is, okay, I want to build a system from data. And I want the final equation to be as simple as possible. So in other words, if an equation has a lot of terms, I will ask the question, can I have fewer terms, fewer number of terms, but I'll be doing pretty much the same thing as the system that have a lot of terms. Okay, so let me illustrate this. Let's say this is the system that we try to approximate. Let's say we have 3 variables, x, y, z. That means the derivatives. Okay, we're working on the differential equations. Right? Okay, what I want to do is let me create a library. What is this library? These are the terms that can happen in an equation. I will put down all the terms that I think will be useful for the description of my dynamics and capacity. I don't have the equation. Remember, I don't have the equation. Okay? I just try to guess according to my knowledge or previous experience, what are the terms that are essential to include in an equation so that I can have a governing equation for my dynamical system, right? Okay. So what is this? This is some parameters. The purpose is I want to pick as few terms from the library as possible. Okay, that's essentially what it means. This is some experiment done by a group of researchers. Okay, this is the original system of the Lorentz system, a highly chaotic system. Right? Okay, this is the reduced order model. Look at the result; they are very similar. So what do we have? This is the original system. This is the reduced system. Right? So in other words, we are able to simplify the original system, but I'm still keeping the salient features of the original system. So that's good. So we can do model dimension reduction. We simplify the equation. When we can learn the equation and simplify it. Okay, as I said, there are other methods. The Gaussian approach is another method. Okay, we look at it as a mixture distribution, and what we want to do is to learn the probability distribution of the strange attractor of a physical system. When we trace the development of thing, I have a trajectory, right? And then I will ask, how would the trajectory converge? It will converge something, right? And we want to study this. Okay, this is another approach. We use neural network to do it, right? As you know, neural network is a black box approach, right? Somehow I have y, which I want to predict. So y is equal to f of x. Right? What is neural network? I don't know the f. I don't know the mapping from the input to the output. I have no idea. I just have data. I have input, I have output. So I ask a question, what is the mapping? Right? Don't know. So that's why we call data-driven learning. I have the input, I have output of the system. Based on this, I want to find out f. So essentially, most of the neural network approach is functional approximation. I don't have the function. I want to approximate this. And this function is highly nonlinear. Okay, I don't know. Okay, this is another thing. I will skip all these technical details, and I want to go into this. This is some. How many of you have worked on neural network? Okay, good. This may be the most popular neural network. It's a multi-layer feed-forward neural network. We have input. Oops. We have input, we have output, and there's hidden layer. Okay? Deep learning. What do you mean by deep learning? It means that we have a lot of hidden layers, right? Many hidden layers. The more you have, the deeper your network is. And that's why you go deep learning, right? Okay. Of course, there will be some research. Do we really need that many layers? Right? That's a theoretical question. But somehow it works. It works, okay? And okay, let me skip all this thing. The whole idea. This is the original system. I want to create a neural network. So this is the expected system output. This is the output from the neural network. I want the square of the difference. the sum of the square of the difference to be as small as possible. What is it when you look at it? Regression. Least square principle. But why do we need neural network? Because for one, we don't know the function. For two, it's highly nonlinear. Okay? So if it is linear, use ordinary regression. Don't work on neural network. Don't copy things. The only reason that we want to use neural networks, for one, we don't have the function. For two, it's highly nonlinear. Right? All those activation function, you use it because it is nonlinearity. Okay? We want to bend the linear trend to curve so they will fit the data best. Right? So that's the whole idea behind this. So these are the process. Okay. Now this is another type of neural network. It's called autoencoder. So why do we need this? That's what I said. A lot of time is nonlinear, the system. Okay. The singular value decomposition is a linear. It's for linear system. Right? So if it is we have nonlinearity, how do we reduce the dimension? Maybe the neural network approach said that we have an idea. Use the autoencoder. So what means is have the input. I project this to a hidden layer, which has fewer variable, a lot fewer variable. So I reduce the dimension already, right? So I need another mapping. Once I got this, then I want to project it back, right? To get something that is very similar to this. Right? Okay. So how do we go about doing this? Look at this. This is what we just looked at. Is the sparse regression problem, right? So once we project this onto this hidden layer, and then we said, what is the governing equations, which have much fewer variables than this one, right? So in other words, we're combining two things. One, nonlinear dimension reduction, and two, learning the system, right? Okay. So we call this, group of researchers call this autoencoder plus Cindy. Cindy is just the regression problem that we look at, sparsity for sparsity thing, right? Okay. I will skip all these. This is how we compute this. Even though this looks complicated, what I would like you to look at is the idea. Okay. See, we have the autoencoder. So we have a loss. Right? We map something from the original back to the output. Right? Go through to what? Go through two mappings. These two mappings. Right? So this is the what we call the autoencoder loss. That is, I use this autoencoder to approximate the output, and I want this to be as small as possible. So this loss is what we call the autoencoder loss, right? Okay, and we use this. This is what we call the Cindy loss, the regression problem based on sparsity, right? Remember, after we project onto the hidden layer, we want to learn the model with respect to the latent variables, not the original variables, the latent variables. This representation will create some loss. We want this to be as small as possible, right? And this third term is what we call the consistence loss. That is, I want to ensure that the model output is as close to the original solution at some chosen points in space and time, right? So in other words, this guarantees that the estimated output is close to the output that we expect from the system. And this last term is called sparsity. We want it to be as sparse as possible. What do we mean? As simple as possible. We're just picking a few number of terms in my equation to do it, right? Okay, so that's the whole idea behind this neural network approach, right? Okay. Now, what I just gone through is with dynamics, we don't have equation, we just have data. So we look at the data with complete observation of the system. So in other words, we can get data about the behavior of the system, right? And we say, okay, can we come up with an equation and further reduce it? And we said there's a neural network approach, there's the regression approach, and that's the Gaussian approach, okay, the Gaussian approach. Okay, 3 approaches. Now, one interesting thing that I didn't touch on is, I think it's very essential in data-driven learning. A lot of time, because we don't have any idea about the system, I don't know how many variables there are. Even though if I know that there should be n variables, but I don't have a complete observation. Oftentimes, right, in our research, we don't have observations for all variables that we think are essential to describe and simulate my system. I just have partial information. Maybe even I have just one variable, and n minus 1, I don't know. Can I still do data-driven learning? The thing is, yes. We can use what we call the delay embedding. Okay, so this delay embedding is, I don't have time to go through it, right? Delay, okay, we want to embed the incomplete system into higher dimension, so that can reconstruct the whole space of the system. And the nice thing about this is, it's guaranteed by topology that I can project it back to the original variable, and I can even find out the behavior of those variables that I don't have observation for. That's very essential for me, or to me, right? Incomplete observation. Can I still do data-driven learning? Okay. The idea is we can go through what we call the embedding, delay embedding. Right? So there are theorems that guarantee that we can do this, right? From topology and from time series. Okay. So I don't have time to do this. Let me look at my time. I actually don't have time to do it. Okay, and it's 11:30 already. Okay, now how should I go about doing this? So many things. Okay, now let me try to finish in 10 minutes. So we have some time for discussion. Right? Now this is an essential thing that I think for data-driven learning. That's what we said. Neural network is a black box approach. We get the result. It's very difficult to interpret. Right? There's no theory in the neural network. What we do have is connections, like the mapping that we approximate. But what does it mean? What are we learning in neural network? The parameters. What are the parameters? The connection rate, right? From one neuron to another neuron. So what I have approximated is the mapping, all the connection weights. How should I interpret these connection weights? What is the interpretation for the threshold on which we can decide whether we can excite a neuron or not? And what's it to do with the thing that I want to study? No theory in it, right? And I cannot guarantee that the result that I get from neural network satisfy the conditions required by a theory, right? So can we inject theory into data-driven learning, particularly for neural network? The answer is yes. We can inject theory into my data-driven learning so that my results can be more interpretable. The intelligibility of my approach will be higher, right? So that is in physics, because physics theory informed neural network. In urban setting, we consider urban theory informed neural network, right? Okay, briefly go through it. I skip all this, and I want to give you an idea. Okay, well, skip all this technicality. Okay. With respect to differential equations, let's say my system is governed by some differential equations. What do we need to solve differential equations? The boundary conditions, right? The initial conditions. So at least for my data-driven learning, I need to require the result to satisfy the boundary conditions, the initial conditions. Okay. You know, initial conditions is very important, particularly for chaotic system. What is a chaotic system? It means that it is very sensitive to initial conditions. Right? A slight difference in initial conditions will take us to completely different trajectories. That's why the system is chaotic, because it's very sensitive to initial conditions. Right? So that's why we want to require the system to satisfy the initial conditions at least, and the boundary conditions, right? So that I'm more comfortable. The data-driven learning satisfy my theory, right? Okay, to a certain extent, I still cannot guarantee that it's satisfied completely because it's built into the loss function that I want to minimize. Right? I just want to make it to satisfy my initial condition and the boundary condition as much as possible. Okay? Okay. That's essentially what it means in here. So we have a loss function based on theory. We have a loss function based on boundary condition and initial condition. And I want to form a composite loss function. I want to minimize these two loss simultaneously. Right? That's the whole idea. Okay. Okay, these are the different loss functions. This is solving the wave equation. Okay. The input, just maybe the spatial coordinates and time. Right? The output is this equation that I want to solve. Right? Okay, I make a P4 neural network. I can calculate all these derivatives, partial derivatives, by automatic differentiation. So the advantage of this P4 neural network is the derivative will be automatically calculated in the learning process. So this is the automatic differentiation. So we construct a loss function due to theory and due to initial boundary conditions. And then I optimize the whole thing. That's the whole idea. Okay. What I have done is I have injected theory and conditions into my data-driven learning process so that I can say that the learning result will be interpretable and it will satisfy my theory. Okay. Okay, that's I skip all these. Okay. Once we have this, we can solve the fourth problem, the inverse problem, and discover equations. I will skip all this because I have a lot that I would like to convey to you. Okay, we can have solve this traffic condition problem through something that we done for the theory-based neural network approach. Okay, we build theory into it. Microclimates. Okay, you know the fluid dynamics. We have a Navier-Stokes equation. Okay, we can use it to simulate microclimate. Okay, and we can do it by theory-informed neural network to do it. Okay, these are examples. Okay, that's what we have done. Urban dynamics, we want to uncover the governing equations from data. Okay, once we can do this, we inject theory into it. We can solve the Fourier problem, inverse problem, equation discovery problem through neural network. Again, I can hybridize it with sparse regression with regularization. Okay. The PDE all built into it. And then we have a loss function that we want to minimize, and then we want to reduce the dimension. Same thing, because the whole idea, I don't care whether it is theory-based, data-driven, always the case. Okay. Once I get the solution, I ask a further question. Can I simplify it? Can I reduce the dimension? Okay, so that's essential. Okay, so now what I've done are these. Okay, we have done this part. How about this part and this part? I'll be very brief. Okay, I can visualize this network, group calculation, then we study all these dynamics about network, right? And we skip these because I want to get to something. This is a three-dimension thing, okay? The percolation theory, okay, still the theoretical solution for 3D percolation is still not completed. Right? People still search for it. 2-dimension, yes. 3-dimension, difficult, right? Okay, and what we want to do is in our social network analysis. In percolation, we want to ask, under what situation will the large component come out? What does it mean by large component? A lot of people are connected into a large subnetwork. Okay, so under what situation will large component exist? Maybe you want to ask, I look at the whole society, under what the situation will a lot of people be connected together, right? Okay. So very interesting thing in here. Okay, now I would like to just draw a few slides and then I will finish. To me, the whole thing is all we need to get is the macro and micro dynamics, right? Macro and micro dynamics. Okay, several things. Do we have a micro foundation for my macro phenomena? In other words, if I have macro equations, would this emerge through, for example, agent interactions? I want to study from bottom up. The macro is from top down. Can I obtain the macro from the micro? Maybe that's what we are interested in. Okay? If I look at my whole system as a multi-agent system, would macro emerge from interactions among these agents, right? Okay, so that's what we want to do. Now this is a thing that I want you to pay attention to, okay? Let's say I have a macro dynamics, I have micro dynamics. Okay? And can I obtain the macro from the micro? Can I decompose the macro so that I can get the micro? Sometimes we want to make it simple, meso dynamics. Okay, micro may be individuals, macro is the whole society. Meso, what are they? Different social organizations, different groups, right? Okay, so in other words, we are looking at dynamics from the perspective of granularity. How I granularize my system. okay, from the very individual to the whole system. Okay? I can have different levels of dynamics. The whole idea is how these dynamics and complexity translate from one level to another level. Okay, that's the thing that I want to drive home for. Okay, on this, in terms of micro, essentially the way to go about doing this is through multi-agent system, right? When the agents interact according to protocols. Now, what I would like to call your attention to is all this multi-agent system. Okay, we have multi-agent system for a long time, but these multi-agent systems are not flexible. They don't have that much of intelligence. What we need to do is to can I instill intelligence into my agent? Okay, the canonical multi-agent system is I give a communication protocol, some few rules to each agent, and then they interact according to this communication protocol. But this is not enough. There's no intelligence in it. I want the agent to be flexible, to be able to what? To cut lies, to remember, to reflect on my experience, right? To be able to update its own knowledge and to do planning. That's what we want the agent system to be able to do. Okay. So to do this, what does it mean? We need the power of generative AI. Okay. This is what we call AI agentic system. AI-driven agentic system. So essentially, what we want to instill into the agent are the collision, memory, reflection, knowledge updating, planning, right? To make my agent more intelligent. So that's the whole idea. What are we looking for? The LLM, large language model, right? ChatGPT, DeepSeek, whatever. DeepSeek is essentially a distillation from the large language model, right? Okay, so we want it to be able to do this, right? Okay. Now, because I said, is digital twin good for urban citizen science research? So we try to think of economics, right? Let's say we have aggregate economic phenomena, behavior. Okay, I have interactions of agents. What can I do? I have macroeconomics and microeconomics. Can I build a bridge between these two? Okay. For economics, I ask whether there's a micro foundations built on humanity in economics. I want to instill individual value system, behavior into my economic system, right? So then I can play around boundary rationality or even irrational behavior, right? I can make my agent to be able to do this. So in other words, we create a human touch to it. So we can simulate and assess individual behaviors. What is it for? In economics, we will be interested in market dynamics, individual behaviors, system equilibrium, effectiveness of economic policies, intervention measures. Something wrong with my economic system, I do want to do some intervention. I want to create some economic policies so that I can steer my system out of the chaos or out of trouble. Right? Can I do this? Under various scenarios before actual implementation, That's why I think digital twins will be good for social science research. It will allow us to evaluate the consequences of intervention before it is actually implemented, because we cannot do experiment with human system, right? We cannot do this. How can we do it? If I can build my system according to, for example, multi-agent system, I can instill all these capabilities into the agents, and then let them, and then I ask, okay, what would happen if I implement this policy? What would the result be? And then you will feel more comfortable and confident to implement the system, right? Okay, that's okay. What about social domains? Oh, simulation, social networks. We may be interested in opinions, crowd behavior, organizational behavior, spread of culture, even epidemiology, right? Spread of disease through social network. Right? Okay, so if my agent can be socio-cognitive, have these capabilities, we can simulate human response and social policy again. We may have social intervention that we want to implement. Again, we cannot do experiment with in human systems. So can I do it with the multi-agent system so that I can evaluate the possible consequences of such interventions? Okay, so we can play with this. So for this, I think particularly on the micro perspective, the digital twins are good for this kind of investigations. Okay. Of course, you have to look at potential risk, all those risks that come with LLM, right? Hallucination, data poisoning, opinion bias. It is not special to digital twin. It's a general situation, right, for using LLM. Okay. My question is, these LLMs are really not the way that we think, the way that we learn language. I wonder whether we have a better model instead of LLM. LLM is essentially pattern matching, pattern recognition kind of thing. We vectorize our words, okay, and then we match pattern. Essentially that's, but that's not how we think about things. Do we need a clever model? Right? So, but that's for future. Okay, issues, all these. I will skip all these. These are the potential problems. Scalability. Look at the multi-agent system. All these multi-agent systems are toy problem. Several hundred agents, several thousand. How many people do we have in Hong Kong? Several million. In big cities in China, tens of millions. Can I simulate the whole thing? Okay, scalability. Can we do it? Okay, there's something that we don't be too enthusiastic about multi-agent system. Are we solving our real life problem, or we are solving the toy problem? Okay, so we have to consider: should we model individual or groups of individuals to make it simple? Okay, that's something that we need to think about. Latency, that is, how fast do we get the response, right? Okay, so that depends on how fast can we calibrate the system. Robustness, would the thing that I did for this system be transferable to other situations, right? Okay. Dependence on the external modes. It depends on LLMs or small language models, okay? But we depend on this. Do we need to do some other things? Interpretability, how to interpret the result of the multi-agent system, right? Okay. Convergency, think, okay, let this simulate interactively. What would they converge to? is there a convergency problem that we need to think about, right? Okay. Lack of benchmarks up to now. We don't have good benchmark to test whether my multi-agent system is correct or not. Benchmark in terms of data, in terms of actual examples, right? Okay. I will skip all this. Too much. Okay. Interoperability. Now, what I would like to finish is with this one. To me, okay, this is what digital twin is about. We have the physical twin, our physical system, right? We want to build a model for it. And through this model, this is some certain degree of abstraction about the build models. We somehow have to abstract our physical system, right? Look at the essential things. So this is the abstraction formulation. Once you look at the model, we can simulate, predict, optimize, control. Right? However, there's another aspect that we have to look at, the data. Okay? From physical system, we have all this sensing, observation, data streaming. We observe from a physical system and get a lot of data from it. But from data, we have representation, visualization, right? A lot of time, a lot of the digital twins nowadays work on this. How to represent my physical system, how to build the virtual replica of system. Okay, to me, it is only this small part. It's not enough. Right? The theory. For data, there's interaction, right? For data, we can do learning, data simulation, another important aspect which I don't have time to go through. How to update my data, how to update my physical twin. And then from model, we can actually generate data. Sometimes in the learning, we don't have enough data, but we can use model to generate data for my training, okay, for my learning. Okay? That's something that needs to go. So I call this three-way interoperation among these three things. Okay. Whoops. Well, I don't skip all these data simulation and other thing. Okay, that's what I said. Based on the definition, I come up with this definition. Okay, essentially these parts are the same. In place of bidirectional interaction, I call it trilateral interoperation, just like trilateral interoperation that we have between the model, the physical twin, and data. Okay, and between each two, there are bidirectional interactions. Okay, more complicated than this. Okay, I'm going way over time. I have some urban sensing, how to build sensor network to collect data. Okay, how to error. Right? Error. If I error in my data, how would it propagate to my output? We have to be able to trace it to make my prediction accountable. I will tell my user, okay, can I create some bounds for my statistical bound for the accuracy of my estimation? We need to do this to make our learning accountable. Okay, so it's another aspect. Okay, error comes from two things: from measurement, from learning. Right, learning, there's a log function. And the data, if data f, okay, what is how to propagate data? Propagate errors. Okay. This is a typical thing. So this is a neural network, right? this is the measurement, the data with what? Noise. Data with noise, and then I use neural network to learn the thing. Neural network has error, so we have 2 errors. And then we need to be able to propagate error in data and error in learning to the final product. So we can account for my learning process. Right? Okay, that's it. So I briefly go over this. Okay, that's the whole thing. Now, the direction for further research, I have no time to do it. But if you're interested in it, I encourage you to read this book. This just came out this month. Okay, I wrote this book. It's called Digital Twins of Cities. The subtitle is Modeling Urban Dynamics and Capacity. Okay, I've taken more than enough time. Okay, sorry about this. And I will stop it here, okay, and see whether I can entertain any questions.
Okay, thank you very much. And this is a very informative talk. So I guess that because Illuminator will have a class here, but so maybe 2 or 3 questions, quick questions. Okay, so any from the online audience from the room? So you know that okay, ready.
Okay.
Well, first of all, thank you very much. It was impressive. I think that's the only word I came up with. But when you were speaking about this last part, the error not only from the measurement of the data, specifically when doing urban development, at least the case of many countries that are still in development, we usually do not have like a city planification or a urban plan, and people just start like building their houses or their towns as they can. Like I can think about like many methods we can use to gather that data, but how can we change the digital twin to give them more information about new patterns? Like let's say we already have a digital twin of Hong Kong, and something changed and people start just like building their own houses because everything is super expensive here. Mm-hmm. So how can we input that new information or that new element into the system dynamic?
Okay. Good questions, and I have to go back. I cannot go back. Try. Okay. This is the part that I didn't have no time to go over. This is actually the data assimilation part. Okay. I built a digital twin, and I want to be able to update it, right? Because things change. The environment can change. A lot of things can do. What you said, new things come up. Okay. And how can I update my system? So this is called the data assimilation. Okay. Essentially, this is my system output in the previous step in time. K is time. K minus 1 means the previous step, right? Okay. Then I can predict. I have the equations already. I can predict a system state prediction, right? Okay. Of course, this has error. So I have to take this error into account, and then I can approximate the system state. Right? This is the prediction based on my system. I predict what it happens. However, my prediction may not be correct, right? So I have observation at the next point in time, okay? And I can update my estimation. One common method is called Kalman. filter, right? We do common filtering, and then I can have estimation for the next point in time. That's essentially the idea. The whole thing is, if you have a building thing, I have a governing equations or some governing mechanism on it. So I have observation over time. So the digital twin should be able to update itself, because digital twin itself is a dynamical complex system. To me, it changes also, right? It changes also. So it changes according to my updated knowledge, according to my most recent observation. Right? Actually, that's how we send the rocket and the spaceship to the moon. Right? We will keep on updating its trajectory, right, through observations. That's essentially what we need to do. Okay, on the conceptual point of view.
Thank you very much.
Okay. Yes. Okay.
Thank you. Sorry that I couldn't come here earlier, but I have been listening to your talk from beginning to end online. And then I have been listening to all your talk, which is wonderful, and thank you for the talk. Also, congratulations on the new book that is coming. I can see that digital twin that has been, a lot of people are working in this field, but I can see that you have done obviously at least one step further to looking at the modeling aspect, the mechanism, theoretical aspect, as well as how it understands the cities, where a lot of digital twin model has been actually really looking at viewing as the first step, like how we can see the cities, how we can look at the different aspects, rather than getting into understanding the mechanisms. So in that sense, I certainly want to read your book, but I also want to hear from you what you can suggest in terms of the current work or practice in developing digital twin modeling.
Okay.
Thank you.
Thank you for it's a good question. Okay. Let me tell you the background of my research. Actually, I didn't know anything about digital twin 2 years ago. I didn't pay attention to it at all. But I listened to a talk, and I listened to several talks afterwards, and I found out that a lot of work place too much emphasis on IoT, on information technology, on, as the professor said, on making a digital replica of the physical object or system that I'm looking at, right? It's on display, visualization. To me, it's not enough. That's what triggered me to do research on this. To me, okay, if this is a digital twin, we're talking about virtual reality. Well, we just look at it, okay? But what do we want to do with it? It has to add value to my existing knowledge, right? So it has to be able to help me to do analysis, simulation, prediction, and control of the system. How can we do this? We need theory, right? We need theory to guide us to do it. For example, if I want to study land use changes, I need to know the theory behind land use transition, right? Otherwise, how can I simulate? How can I predict? How can I control without knowing the governing mechanism, without knowing the governing equations? That's what I think is we should inject theory into digital twin construction and its usage. Right? Without theory, we cannot get too far with digital twin. Right? Just visualization display. Okay, we want it to work for us. Right? Work with us in terms of theory development, in terms of practical applications. Right? In my book, I outline a lot of direction for future research. Okay, so one of it is the multi-stakeholder decision making. Right? How can I build multi-stakeholder decision making into digital twin? Let's say in the social domains in economics, okay, in geography, in architecture, or how can I do this? So to me, theory is the most important thing in digital twins, not the information infrastructure. They're essential, but not the most important thing. So it would be nice if we can integrate theory and data together to construct digital twins. That's the way I look at it. Okay, if you're looking for research problems, I encourage you to read my book because I raise a lot of research issues in the book along the delivery of how we should go about developing digital twins. There are so many problems that we can work on, particularly from the interdisciplinary perspective. Okay? We need to transcend boundaries, okay, to several disciplines work together.
Okay, thank you very much. I guess that we have to stop here. But unfortunately, you can always find Professor Liang on Sundays at the tennis court. So thank you again. This is a very important talk. I learned a lot and also remained a lot of big problems when my experience would start from modeling, and then because later we have big data, so I'm working with data. So you may probably that you don't have time to notice that this is a not trivial question. It's a very important question to bridge the modeling approach and the data-driven approach. So you're really encouraged to read the book, even if it's not so that cheap. So, but I guess that you can get the book from the library, okay? And also yeah, okay. So also thank you for the online audience. So we will see you next month, and because this is a monthly webinar, okay. So thank you again for
okay, thank you. You're welcome to.
Yeah.